Okay, now for the second method that we use for finding the partial fraction expansion when we have complex roots. Um, in this method, we use a property of polynomials, and that is the following. Let me write this out. That if we have two polynomials, let's say the polynomials are a let me give it like a cubed x cubed plus, I said a cubed, I mean a sub 3, a sub 2 x squared plus a1x plus a0. If this polynomial, whatever it might be, equals this polynomial, where I have b sub 3 x cubed plus b sub 2 x squared plus b1x plus b0. Okay, if I happen to have two polynomial functions and the polynomials are equal everywhere, the only way I can have two polynomials be equal everywhere is if the coefficients of like powers are equal. So if this polynomial as everywhere gives the same value as this polynomial, it must be true that a3 equals b3 and a2 equals b2 and so on. And we get a0 equal b0. Okay, so the only way two polynomials can be equal is if coefficients of like terms are equal. We can't have two polynomials be equal if the coefficients of both are different. Okay, now with this in mind, let's look at this second method for doing partial fraction expansion here. Let's suppose we have this function. It's the same function we had in the previous video, this function right here. Only we want to break it up as follows. We want to write it as a divided by s plus 5, which is this factor. And this factor, we don't factor it into its two complex factors. We leave it as a quadratic polynomial. And it turns out that the form that is appropriate is this form here. So we have bs plus c all over s squared plus 4s plus 5. Now we want to find a, b, and c here. So to do this, we multiply both sides of this equation with this equal sign. We multiply both sides by this denominator right here. So when we multiply this term by s plus 5 times s squared plus 4s plus 5, then that will cancel out with when we multiply by this factor, it cancels out with that denominator, leaving s plus 3 on the left side of the equal sign. But on the right side of the equal sign, we have s squared plus 4s plus 5 times s plus 5 times this term, a over s plus 5 plus bs plus c. So that's what we get when we are multiplying this function right here by that denominator function. Okay, now we continue to multiply it out as shown here. And then what we do here is we group together all the coefficient, all the terms that have like powers of s. So we group together all the s squared terms, and that's a plus b. We group together all the terms that are multiplying a factor s, and that's 4a plus 5b plus c, and then we have this as a constant. So how does this work? Well, when we multiply this by that, you see that when we're multiplying here, the s plus 5's cancel, leaving us with a times s squared plus 4s plus 5. And then when we multiply this thing times this fraction, it's the s squared plus 4s plus 5's that cancel, leaving us with s plus 5 times bs plus c. So now we multiply this through. As squared, okay, and then we have the bs times s gives us a bs squared. So that's where the a plus b is coming from. Let me multiply this out so you can see right here. Okay, this becomes as squared plus 4as plus 5a here we get bs squared here we get 5bs and then we get c times s plus 5c. Now we group together all the factors that are multiplying s squared. That's this one and this one. So we get a plus b times s squared. We group together all the terms multiplying s. So this becomes 4a. Okay, so we've got rid of these two. So then we have 4a, got rid of that, plus 5b gets rid of that, plus c, and all these multiply s, and then we pull together all the constant terms, which is 5a plus 5c. So you see, this is exactly what this expression is, right here. Okay, now, so on the left side of the equation, we have s plus 3. So we're saying that s plus 3 is equal to this. How do I write that down here? S plus 3, let me say over here, this equals s plus 3. Now remember I said we have two polynomials that are equal. We have this polynomial over here, and we have this polynomial over here. So this one has no second order power of s. So that means that a plus b must equal 0. This one does have one multiplying s. So that means that 4a plus 5b plus c is equal to 0. I'm sorry, I said equal 0. I meant equal 1 because the coefficient here is 1. And then we have a constant. The constant is 3. Here the constant is 5a plus 5c. So we have that 5a plus 5c equals 3. So this is all summarized here in this little chart here, where we say, okay, the second order coefficient on the right hand side is 0, on the left hand side it's a plus b, so 0 must equal a plus b. We have 1 must equal 4a plus 5b plus c, that's this. And we have that 3 must equal 5a plus 5c, which is this. Okay, so that's this chart here just summarizes that. Okay, now we have 3 equations and 3 unknowns. Well, right off the bat we see that this means that b is equal to negative a, and we have the 4a minus 5a plus c is equal to 1. So we can solve this. We have two terms with a, so we have 4a minus 5a plus c is equal to 1, and that means that c is equal to a plus 1. So then we look at this last equation. We have 5a plus 5c is equal to 3. That's what this is. Then we can substitute c is equal to a plus 1 We substitute that in right in here. Okay, so 5c becomes 5a plus 5. So we have 5a plus 5a plus 5 is equal to 3. 5a plus 5a is 10a. So we have 10a plus 5 is equal to 3. Now we solve for a, and we get a is equal to negative 2/10. We have b is equal to 2/10 because we can solve for b as negative a. And then we solve for c using the fact that c is equal to a plus 1. So this then, right here, is the solution for our three coefficients. Okay, and this is our second method for doing the partial fraction expansion when we have complex coefficients. And you will see that when you plug these in for a, b, and c up here, we get the same solution that we found in the previous video. Okay, so that's all for now. Until next time.